back to our channel. So in the previous sessions we have seen the AVL trees and different rotations that can be performed on AVL trees. So first of all we'll recall the previous concepts. So first one, what is an AVL tree? So AVL tree is a self-balancing binary search tree. So that means it should obey the property of binary search tree as well as it should obey the property of AVL tree. So here the property of AVL tree is every node should have a balancing factor with a value -1, 0 or 1. So how to calculate this balancing factor? So balancing factor can be calculated as the difference between the height of the left subtree and the height of the right subtree. Right? So if for every node we have to calculate the balancing factor, and that balancing factor should be either 0 or 1 or a -1. Right? So which violates this property, that is called as imbalanced binary search tree. It's not an AVL tree. Right. So if you are inserting any node into the AVL tree, or if you are trying to delete a node from the AVL tree, then there is a chance of violating this rule. That means if you insert an element into the AVL tree, then the balancing factor may change for that particular node. Right? So that means the tree may be imbalanced tree. So we have to convert that imbalanced tree to balanced tree. So for this conversion we are supposed to use the one among the 4 rotations which we have seen in the previous sessions. So I will give you the link in the description section. Just follow that before watching this session. Right? So there are 4 rotations, that is a LL rotation, RR rotation, LR rotation, RL rotation. Right? Now let us see an example and let us construct an AVL tree for the given nodes. Right, now let us see this example. Let us take these elements and now we have to construct the AVL tree. That means inserting one element after another. And we have to take care, or we have to remember that after inserting an element we have to check for the 2 properties. One is the binary search tree. That means all the left side nodes should be less than the root node and all the right side nodes should be greater than the root node. That is the property we have to remember. And then we have to remember the second property, that is a AVL tree property. That is, for every node the balancing factor, that means for every node the height of the left subtree minus height of the right subtree must be either 1, -1 or 0. So 2 properties you should be remembered, that is a BST property. Second one is the AVL property. Right? So first consider the 20. So first step, so 20 is a root node because empty. So here AVL tree is an empty. So 20 is a root node. Now second step, insert the 30. Insert 30. So after inserting that 30, so based upon the property of BST and AVL tree. So based upon the BST property, 30 is greater than 20. So 30 should be inserted on the right hand side of 20. Right. So this is the first one. Second one, AVL tree. I mean AVL property. AVL property means this balancing factor should be either 1, 0 or -1. Right? It's a balancing factor. So balancing factor means height of left subtree minus height of right subtree. So here the height of left subtree, so there are no nodes, so 0. The height of left subtree is 0. Height of right subtree for this 20, right? For this 20 there is only one node. So 0 minus 1, it is 1. The balancing factor is -1 for 20. For 30, it is a leaf node. So it is a leaf node, there will be no right children and left children. So that's why the balancing factor will be 0. So -1 and 0. So both are within the range. So this is also correct. It's a balanced, right? It's a balanced. Third step, we have to insert the third element 80. So 80 is a greater than 20. So it should be inserted on right hand side. So in the right hand side again there is a 30. So in the 30 also 80 is greater than 30. So it should be inserted towards rightmost of this 30. So after inserting this one, the tree will be 30, 80. Right? So coming to the third one. So this is about the BST. This is a binary search tree. Now we have to go with the AVL property. AVL property means we have to find out the balancing factor. So from top, always calculate the balancing factor from bottom to top. So bottom to top, this is a leaf node. So the balancing factor will be 0. So this is a node with only one element, that is also rightmost element. So 0, left hand side there are no elements, right? So balancing factor is equal to 0 minus 1. This is minus 1. And again here also there are no left hand side elements, only the right hand side elements. What is the height of this node? Right subtree, height of right subtree is 2. Right? So height means the longest path from root node to, that node to leaf node. So 2. Here the balancing factor is 2. Left side balancing factor, left side height is 0. So 0 minus 2, it is minus 2. So which violates the AVL property, because for every node the balancing factor should be either minus 1, 0, 1. Here we got the 2. The balancing factor is 2. Right? So here this is an imbalanced tree. So this is an imbalanced tree. So what we have to do, in order to get this imbalance to balance, we have to use one among the 4 rotations. What are the 4 rotations? One is LL, RR, LR, RL. All these are the rotations. So based upon the situation, we have to apply this one. So this is the right skewed. So when we got this imbalance, whenever we are inserting an element to the right subtree towards the rightmost element, so that means this is called RR rotation. So we have to apply the RR rotation. So after applying the RR rotation means we have to rotate this towards the left side. RR means towards left. So we have to rotate in this direction. So after rotating this one, we will get, so 30 will be moved here, 20 will be moved towards the left, 80 will be moved towards right. So after applying the RR rotation, we will get the result as this one. So here now we have to calculate the balancing factor. So these are the leaf nodes. The balancing factor will be 0, and this is the node. For this balancing factor is left side height minus right side height. Left side height is 1, right side height is 1. So 1 minus 1, it is again 0. So it obeys the property of AVL tree. Right. Now fourth element. So we have to insert the 40, element 40. So now the tree is like this: 30, towards the left there is a 20, towards the right there is a 80. Now we have to insert the element 40. So again that should obey the BST property. So 40 is greater than 30, so it should be inserted on right subtree. And again 80 is the root here, so 40 is less than 80. So here we have to insert the 40 as a left subtree for node 80. Now, so this satisfies the BST, because all the elements of right subtree are greater than root, all the elements of left subtree are less than root. This property is right. Now coming to the AVL property. So coming to the AVL property, we have to find out the balancing factor. So balancing factor for the leaf nodes is 0, and for this node 1 minus 0. So right subtree is 0, so 1 minus 0, 1, and for this one 1 minus 2, because the right subtree for this 30 is 2. The height of right subtree is 2, the height of left subtree is 1. So 1 minus 2, it is minus 1. So all the balancing factors are within the range -1, 0 and 1. So it is a balance. Now coming to the fifth one. So we have to insert the element 10. So same property we have to use. So 30, 20, 80. So towards the left there is a 40, element 40. Now we have to insert the 10 element. So 10 is less than 30. So 10 should be inserted towards the left hand side, left subtree. In the left subtree there is a one root 20. So 10 is less than 20. 10 is less than 20. So 10 should be placed towards the left hand side. 10 should be placed towards the left hand side. Right? So now it obeys the BSD because all the elements of left subtree are less than root element and all the elements of right subtree are greater than root element, right? So now we will go with the AVL by calculating the balancing factors. So balancing factors of this one is 0 and this element is 1 minus 0, 1, 1 minus 0 is 1, this one 2 minus 2, 0, right? So again this is a balanced tree. Now sixth, that means we have to insert the element 60. So 30, 20, 80, 10, 40. Now we have to insert an element 60. So 60 is greater than 30, 60 is greater than root. So we have to insert the 60 towards the right side. So right side the root is 80. So 60 is again less than 80. So 60 should be towards the left hand side of left subtree of 80. Again left subtree we are having 40. So 60 is greater than 40. So 60 is greater than 40 means we have to insert this 60 here itself towards its right side. Towards it right side. Right? So here we are inserting. So again the BSD property is satisfied because all the elements of right subtree are greater than root, all the elements of left subtree are less than root. This satisfies. Now calculate the AVL tree. Now calculate the property of AVL tree. So the leaf nodes, it will be 0 and for this one 0 minus 1, it's minus 1. For this one 2 minus 0, it's a 2. So just stop it. So we need not go with the remaining nodes. So here it violates the AVL tree. It violates the AVL tree. Right? So here we have to stop. So if you observe this one, when we got this imbalance, so this is a imbalance. This is the imbalance tree. Right? So in order to change this imbalance to balance, what we have to do? We have to apply one among these 4 rotations. So here when we are getting this violation, whenever we are inserting an element towards the right side, okay, and see, so here we have got the violation for 80, right? So left side, right side, okay, left and right. So you can observe this one. So this we got a violation. So this is the left node, right node, left node, right node. So that means LR rotation. We have to apply the LR rotation. So this is a 2-step process. So this is a 2-step process. So for the first step we have to apply the step 1. We have to rotate left side. So we have to rotate left side. Left side means, see, this way. So after applying this one, so let us erase this one. After applying this one, we'll get, so 30, 20, 10, 80. Now after rotation, 60 will become here. 60, 40. Right? So this is the first step. So after second step, So what we have to do? Second step, rotate right. Rotate right. So in this way we have to rotate. In this way we have to rotate. Right? So then it will becomes, so 30, 20, 10, 60, 40, 80. So this becomes this one. Right? Now, so again, now we have to calculate the balancing factor. So here we should not calculate the balancing factor because this is a LR rotation. LR rotation means two-step process. So after completion of two steps only we have to calculate the balancing factor. So these are the leaf nodes. The balancing factor will be 0, and for this node the balancing factor will be 0. For this node the balancing factor will be 1, and for this node the balancing factor will be 0 because height of left subtree is 2, height of right subtree is also 2. Now coming to the seventh one. So we have to insert 50 for this one. So 30, 20, 10, 60, 40, 80. So now we have to insert the 50, but it doesn't violate the BST. So if you insert a 50, so 50 is greater than 30, so it should be on the right subtree. 50 is less than 60, it should be on the left subtree, and 50 is greater than 40, it should be on right subtree. Now again calculate the balancing factor. So for the leaf nodes it is 0, 0, 0. For this one 0 minus 1, it's a minus 1. For this one 2 minus 1, 1. For this one 2 minus 3, it's a minus 1. So it satisfies, so it's a balanced tree because for every node, for this one it's a 1. For this one it's a balanced tree because for every node the balancing factor is either 1, 0 or minus 1. Now insertion of a, so 8th we have to insert the 70. So 30, 20, 10, 60, 40, 80, 50. Right? So this one, now we have to insert the 70, that should not violate the BST. So 70 is greater than 30, so it should be inserted towards the right subtree. So in the right subtree 60 is there, so 70 is greater than 60, again we have to go with the right subtree. In the right subtree there is a 80, so 70 is less than 80, so 70 should be placed here itself. So that means it should be placed towards the left hand side. For 40 it is a 50, and for 80 it is a 70. For 80 it is a 70. Right? So this is how we have to apply. Right? So here you can see the balancing factor. So for the leaf nodes the balancing factor is 0, and for this one it is 1, for this one minus 1, for this one 1, and for this one 2 minus 2, 0, for this one 2 minus 3, minus 1. So here it obeys the property of AVL tree. So that's why it is a balanced. So it obeys the BST property and it also obeys the AVL tree property. Right? So hope you understood this example. So don't get confused. So just we have to satisfy the BST property, binary search tree property. So based upon that binary search tree property, we have to insert the node into the AVL tree. That means the element should be compared with the root, and then we have to decide whether it should be inserted towards the left side or it should be inserted towards the right side. That's the first thing. So after insertion, second thing, we have to check for the balancing factor. So whether the tree is balanced or not. So that's the definition of AVL trees, right? Self-balancing binary search tree. So for that balancing factor, we have to calculate the height of a left subtree minus height of the right subtree. So if that balancing factor is other than -1 or 0 or 1, that tree is a imbalanced tree. So for changing that imbalanced tree to balanced tree, we have to choose one among the 4 rotations. So LL rotation, RR rotation, LR rotation, or L rotation. Right? So based upon that thing, so here LR rotation and RL rotation are two-step process. So in the LR rotation, first we have to apply the left rotation, and then we have to, in the second step, we have to apply the right rotation. Coming to the RL, first we have to apply the right rotation, in the second step we have to apply the left rotation. Right? So this is how we have to insert an elements into the AVL tree. So this is simply, we call it as a construction of an AVL tree. Right? So the same process we have to apply while deleting an element from the AVL tree. So after deleting the element, again we have to check for the BST. The same process we will follow, which we have followed in the BST. So deleting an element from the binary search tree, the same process we will follow, but here addition to that we have to calculate the balancing factor, and based upon the balancing factor we have to apply the rotations to make the imbalance to balance. Right? So this is a simple example. So hope you understood this one. So here only 2 rotations are there, one is a RR and another one is LR. Right? So if you take one more example, then you may get a multiple number of rotations. Right? So just keep on practicing this one, and if you are having any doubts regarding the process of this AVL tree construction, so feel free to post your doubts in the comment section, so that definitely I will try to clarify all your doubts. And if you really understood my sessions, like my sessions, share my sessions with your friends, and don't forget to subscribe to our channel. Keep following. Thank you.